Majib Ali from Western University. Here's the outline of this talk. We expect the audience have some working knowledge of C, C++ programming language, and some basic exposure to the message passing interface, or MPI. Why should we care about the concurrent or parallel I/O in parallel computing? There are some issues to address. So consider the scenarios in the parallel computing. One needs to read a large file or write the computed data to a file. The usual workflow would look like this. One process, for example, in the context of MPI, rank 0 reads the file, and rank 0 distributes data to other processes, and then everyone gets work done, and then the rank 0 collects the results, assembles the received data into the global storage, and the rank 0 then writes data to a disk file. Although this is a typical workflow, and the problem with this workflow is as follows. One process, for example, the first process, or rank 0, reads the file. And when the data size is huge, this process needs a huge memory to store the data, especially when we talk about several gigabytes or huge data that cannot fit into the physical RAM. And then the rank 0 distributes data to other processes, and this yields a cost of communication. And then everyone gets a chunk of work share to compute, and it gets work done, and then rank 0 collects the results, assembles, receives the data into global storage. Again, the assembly needs a huge memory because the process will have to collect all the data from all other processes and load them into to fit them into the memory. And then lastly, it will write the data to disk file, and this may take quite some time, especially if there are lots of data to write. Another issue with such unbalanced memory usage is the job when you run your such MPI or parallel programs on clusters. The job will request for per core the max memory needed by the I/O process, and this may result in a longer wait time and it costs more to run. On Gran and Cedar, for instance, the cost is based on the number of cores used and the amount of memory per core. In this case, in the diagram, the max RAM request in this case will be consumed. So on the left, the actual memory needed by individual processes, and on the right, that's the amount of memory will be charged, and the job will be classified on a system. So the parallel I/O addresses these issues with the following benefits. Each process will read just a chunk of the file, and less memory, therefore, is required by the dedicated process or rank 0, for instance. The cost of communication to distribute the data can be avoided, and everyone gets work done, and the collecting and assembling data is no longer required because it's done on each individual processes. And again, less memory is required by rank 0. And each process writes its own data to a file, so less amount of data to write. Therefore, possibly will take less time. And before we go into an MPI, the world of MPI, let's take a look at how we can have multiple processes read data from a single file and write to the same file in a general case. So here's the task. We want to have multiple processes read chunks of data from the same file. Each process reads a chunk of data from predefined locations, and the last process might need to read a little bit more when the total number of records cannot be evenly divided. On the right-hand side, there are we consider two scenarios. Scenario A, data are grouped in chunks, and then on scenario B, data are grouped in chunks but interlaced. So what we need is each process opens the file, and each can seek the position to read the data. And everyone reads, completes, and closes the file independent of others. Now let's take a look at how this is done in C and on Linux. First, we calculated the chunk of data to read. We calculated the start index, I1, and end index, I2. And these two also correspond to the position pointing to the records in the file. And that file to read, let's say it's called the data.bin, or just a binary file. And then the second segment of the code here is we read my chunk of elements. Open the file. Open the file in the read mode, and then I just loop over from the start index to the end index. And for each read, we calculate the offset from the beginning of the file. And we call a system called fseek that will take us to the right position to jump from the beginning to the right position to read. And then we call the function fread to read the data into the variable v. And the amount of data to read is of size float. This is measured in bytes. Okay, and the number of elements to read is 1, and the last element fp is just a file handler. And after we finish this loop, I'm done reading of my chunk, and I close the file. And this is for process me. To read, for instance, to read the second chunk of the data from the file. And everyone else just does the same. Everyone will calculate the start and end index, and then I call fseek, called fopen to open the file, and I called fseek to jump to the position to start a read consecutively, and then close the file. Now, second scenario. In the second scenario, we have the data stored in a file in chunk interlaced. Now, to deal with this, we placed a for loop. This for loop, the outer for loop, will loop over interlaced chunks. And inside this for loop, we calculate the start and the end index of each individual, the red blocks. And then we do the same. We just loop over the records within the chunk and jump to the position to read and read the data into the variable, and then we're done. And in the end, after we're done, and we close the file. And this is how we have multiple processes read the data chunks from the same file simultaneously. Now, writing to the same file. is similar, but needs a bit of attention because we need to deal with asynchronism. So here's the task. We want to have multiple processes write the chunks of data to the same file. So one process creates a file. We need to dedicate one process to create a file, open the file, and then have each process open the same file and write the chunks to predefined locations. And assume there are no overlaps. And each process closes the file and it's done. Again, we consider the two scenarios we've just seen. Scenario 1, we have data chunks grouped in blocks. And at scenario B, we have data chunks interlaced. And here's what we need. We have one process create a file. We have a dedicated process create a file, open a file, and then have it stretch the file to the desired total length. This is important operation we need. And then each process opens the same file and writes the chunk to predefined location. Each process then completes the writes and closes the file independent of each other, and we're done. Now, let's take a look at how this is done in the actual C code. Now, this is a typical multiple process, a single process, single program, multiple data model. We write a code in such a way that we will do different things depending on the process ID. So if my process ID is 1, I will open this file to read. I open the file and using these modes. Okay, this is the we'll come to that during the demo time. We'll open this file to create this. Open the file in the appropriate modes, and the last argument is a mask, so that the file will have to be opened will have the appropriate permission. And the next call, ftruncate, we call this ftruncate to stretch the file into the appropriate desired length. This will be the total length, the total number of records, or total number of total size of the file data in bytes to write. Now, when the file is opened, this of course is empty, and then we call fdopen to associate the file descriptor fd returned by the call to open, and we associated this file descriptor to the file handler for writes later on. Now, if my ID is not 0, and the other, like a 1, 2, 3, 4, or other number, then I'll do the following. I'll wait in the do loop, and first try to check, see if the file is already has already exists. If the file exists, then I'll jump here, I'll open the file to write. Otherwise, if the file does not exist, I'll check the error node, which is set by the call to the system call access. If the file does not exist, I'll sleep for amount of time. In this case, I put 2 seconds, and then we'll wait. I'll come back here and back to the loop. Of course, and now I have this exception handling if the call to access failed, and the file does not exist, then I'll just quit. Okay, this part, else part is exception handling. So I'll check for any other processes, not a 0, except for 0. It will check first. It will check whether the file exists or not. If the file does not exist, then I'll just sleep and come back. And otherwise, we'll jump here and open the file. Even though the file is already created and open, I can still open the file, but open the file in this mode, in R+B mode. R+B mode is to open the file for reading and the writing. Okay. And this is the global view of the code. Multiple processes write data chunks to a data file. And so we have this if branch, and the first is, as I just said, I detect whether my ID is 0 or not. If my ID is 0, I open the file and stretch the file to the total length and get ready to write. And here, if my ID is not 0, I'll attempt to check the file, whether the file is already opened by or created by the first process with ID 0, and then open it if the file exists. Okay. On the right-hand side, I wrote a bash shell script to launch the processes in parallel. Now, I launched the processes. In this case, I decided to have 4 processes, and I launched them in a random order. And here's the call. I called a bash command, chef. Chef will generate a number between 1 to 4 randomly, a list of integers from 1 to 4 randomly. And then I'll do it in the for loop and pick the ID and generate and call this code. This code will pass the process ID to the code, to my source code, and the first code to start is not necessarily a 0, or sorry, in this case a 1 actually. It's not necessarily 1, and it could be in a random order just to test the randomness of or asynchronism of the code. Okay, so this is the source code. And the source code, again, the second part of the source code is, of course, to write the data in chunks to the data file. And this here, it shows the example for the second scenario in which data chunks are interlaced. Okay. We'll do the demo later on after I finish the slides. Okay, so next, let's take a look at how one can use MPI to do the concurrent or parallel I/O. So MPI has a set of functions that facilitate what we want. Each process reads a chunk of data from the same file, and each processor writes a chunk of global data into a file in desired order. That's what we want. So the first example in MPI is a hello world. In this example, first I create a message, hello world, from a rank. I just calculate the rank. I just get the rank. And then I calculate the message size. Now, these 4 MPI calls, the 4 MPI calls are typical calls you need. First, I open the MPI, open the file, and the first argument is the communicator. If you are not familiar with MPI, don't worry about that. Just the first call you need is the MPI file open. To open this file called hello world.txt, and the next argument is the combination of modes, open modes, and the last one is the file handler. And so once we get the file handler, the file is open, successfully open. We call seek, fseek, As we saw previously, the MPI file seek to jump to the location to write. This is important. The conceptual is important. We open the file and jump to location, a predefined location to write the data. And then next, once we are at the right location, we write the data, which is the message. That's what we want to write. And I want to write the data stored in this buffer message, variable message, and the size is message size calculated, and the type is MPI char, which is implied, and status, that's the argument, and the variable contains some information returned by the MPI call, and then a close. Okay, very simple. Now let's take a look at the individual MPI calls. First, the MPI open, and the first one, just the communicator. This F open, or then we'll take a look at what the regular open will look like. So we have actually the first one is the actual element communicator in the MPI world, and the next one is the file name to open, and the third is the file access mode. This is similar to the Unix system call. And the last one is the information, the file handler. And then access mode, we have a bunch of access modes. For details, you would have to look at the MPI man page. And then next, we just compare with the system call open. The system call open will take the first argument as a file name, and the second is the file access mode. You see we have a create, append, read only, and etc. And if you go back and see MPI file open, it has a similar modes, and this sort of tells you where those modes come from. If the first time you look at the MPI, you might wonder where those modes come from. If you are not familiar with the Unix or Linux system call, okay. And then fseek. Of course, we need the fseek to jump to the location we want to read or write, and then the write. And the fwrite MPI file write function is basically a function to write the data into the file. And then lastly, when we're done with reading or writing, we close the file. And we don't need to know the details at this stage. If you want to see the details, you can always see the man page. If you have access to MPI at the command line, if you type MPI, if I type a man and the function name MPI underscore file underscore blah blah blah, then you will see the details of the manual page. The next example is the MPI hello read, and so we have a read and we have a write, and then also we have a read similar to MPI write. Yeah, we'll take a look at the example later on. So next example. This is a bit of a more advanced example. So those of you who are doing MPI but have not used the parallel I/O features would possibly appreciate the convenience that MPI calls provide. So in this example, we attempt to write an n by n array and distribute it on 4 processes to a file. So we have a array, in this case a matrix, for example, 8 by 8 matrix, but this matrix is distributed among 4 processes, and we want to write, we want to have each MPI rank, each MPI process, write its own chunk or portion of the matrix to the same file. So for instance, rank 0 will just write this pink portion, the subarray, to the location, appropriate location of the file. And rank 1 will write as the blue subarray into location 2, and so on and so forth. Now, if you take a look at the layout of the data in the local memory, if it's stored in a column major. Okay. Now, speaking of data storage, there are two types: column major, which is used by Fortran, or row major, which is used by C. In the case of a column major, data are stored in column. So, for instance, the first subarray, the data layout is 1, 9, 17, 12, 25 to 10, 18, 26, and so on and so forth. Okay, they are stored consecutively in the local memory, and so are the data for the subarray on process 1, process 2, and process 3. However, in the global memory, the layout would look like this. They are interlaced. So the subarray, the first column of the subarray is stored in the first location of the file, the memory, and then followed by the first column in process 2. In the subarray held in the process 2, and then again process 0, the second column on process 0, and then followed by the second column of the subarray on process 2, and so on and so forth. So you need to get the memory layout correct before you can do anything. So that adds another layer of complexity. And when you do an MPI parallel I/O. So how do we do this in the MPI? And it turns out that is actually quite simple. The MPI functions give you the convenience. So here's the some summary, the highlights of the MPI code that we need. Of course, you need to initialize the MPI environment. You always call MPI init, MPI const size const rank. And then I come to the real business. We want to calculate the local number of columns, the start column and the end column, and the start row and end row of your local subarray. You need to get that correct. You need to get that the start and the end column in the global, the index in the global matrix, global array. So first thing you need to do is you need to get the start and end indices of local array in the global array correct. And then you need to create the two things. You need to create the dimension of the local array, the first dimension of the local array, and the second dimension of the local subarray. And then you need the start indices of the row, and the start indices of the column in the global array. And then in the MP, you need to place these two MPI calls. You need to create a view of subarray. Just take it for granted. Don't need to know why you need this. This will be another a separate topic. So you need to create a subarray. You need to create a view of a subarray. And this subarray, the arguments are, this is a two-dimensional subarray, and this is the second argument is the global size, global dimension, and the next is the local dimension, and the next are the start row indices, the start row index, and the start column index. And then you put the three other arguments required by the MPI call. And this call will return an object called a view type. And you take that return object and put in the call MPI type commit to commit an object. Once you're done with that, then we come to the regular MPI open. We open the file to read, open the file to write. We open the file by calling MPI fopen, and then we need to call a different function, not a seek. We call it MPI fsetView. Remember, we have an object, the view type. Now this is the time to install the view into the call. What it does is basically it does the seek, and it will take you to right location. And then we place the MPI call write, and MPI call write underscore all means this is a collective call that all the MPI ranks will call this function. And this is pretty simple. You just the first argument is a file handler, and the second argument is the beginning of the data buffer of this local subarray. This is a local subarray. The local subarray followed by the chunks, followed by the chunks of data you want to write. The information of about the shape of the subarray is contained in the object view type. Okay, this is why we create this subarray view. This is view type object. So the information about the shape of the subarray is stored in the view type. And when we call the MPI file write all collective call, all we need to pass to this call is the buffer, the pointer to the buffer, and the total number of elements to write, and the type of the elements, which is a float in this case. And then we close the file. And after that, we just do a cleanup, and we clean up the object, and then we're done. We're done. Okay, so this is the end of the presentation of the slides. Let me just switch to the demo. Now, this terminal, I have a number of examples. Let me just go. Maybe we just want to go through the first example to write the data. To write the data in data chunks into a same file. So in this example, this is a C example. This is not the MPI yet. This is a C example. So what we want to do, we want to write 100. We want to write 100 lines of data into a file. Okay, and each line is just a number. Just make the file, make the example simpler. Each line is a number from 0, 1, 2, 3, 4, and so on and so forth. But this 100 numbers will be written by 4 processes separately in parallel. Okay. So what we need to do first, we calculate the chunk of the size as one of the process to write. So I calculate the start index and the end index. Okay, this is the range of the number I want to write to the file. And then we come to this part, and we open the file. If my ID is 1, I just open this file. Don't worry about this this micro conditional combination printf statement. Ignore that. So we come to the first part here. If my ID is 1, I open the file to write, and the second argument is the file access mode. If you take a look at the main page of open, it tells you what is the file access mode. Mozart. And then the last one is the assess the permission bit properly. And then next, I call f_truncate to stretch the file to the total length. In this case, will be 100. Okay, and then I associate this file descriptor. Now remember, when I place the call open, when I call open, the open returns a file descriptor, and then I want to use this file, but I want to use a file handler to do a higher level I/O. So I want to associate this file descriptor with a file handler, which is FP. And the FP, if you go up, FP is of file type. Okay. Back here. Now, if my ID is not 1, then I'll do the rest. First, I'm sitting in the do loop and just wait and see if a file has already been created. If the file is created, and then I come to here. I just simply open the file for writing. The mode I'm using is R+B. R+B allows me to read and write. Okay, and then it just jump out of the loop. And then this part, everyone does the same, and just loop over the data range and create this the number, and this called fseek to jump to the appropriate location, and then write the number to the file. Okay, so let me just compile the. Actually, I already compiled the file. Compile the file got to be B. I can just simply run the file. Now, to run this file, to run this code, I need to run 4 instances simultaneously. And to add a bit of asynchronous to the case, I did this. So this is the shell script. The number of processes I set to 4, and then I set the process ID a number, and randomly I'll generate a number between 1 to the 4, and this call shove will return a list of IDs between 1 and 4 randomly, and then I start this program. This program I compiled is called bin_p write_c. I pass in 2 numbers. First, I pass in the process ID, which is a random number between 1 and 4. And the second one is the total size, which the second one is the number of processes, which is 4. And then I wait for randomly wait for 5 seconds, between 0 to 5 seconds. Okay, so let's just run this code. Okay. Now, as you can see, this time it starts in the in the right order. It started process 1 first. Let's try it again, and let's see again. Okay, started process 1 first. Maybe I try it again, then I try to see if it can start something else. Oh, wow. Okay. Anyway, just to see the content, and so after I run this program, it generates a binary file. In this case, the M records, the multiple records, and I use another file to read. Now let's take a look at the read part. The read part is done by the source code bin_parallel read. Now the parallel read code, the source code, is much simpler. All it does is to calculate the chunk calculate the chunk to read, and calculate the start and the end index to read, and then just open the file. Because opening the file can be in any order. So we don't have to dedicate a particular process to create a file, to open the file first. So anyone can open this file and read and complete. So the read part is quite simple, straightforward. So we're just sitting the loop, and we loop over the data range between I1 and I2, and seek to jump to the right location, and then read and print. Okay, so let's take a look at the code. And again, the read is done through a shell script. Again, because I need to start 4 processes to do this example. So I just write a shell script and loop over for 4 processes. To generate 4 processes then to the read. So this is what we should see. All right. Okay. So the result is this. Each process reads the data chunk correctly, and the first process reads the data from 0 to 24. So the total numbers is 100, and the first each one gets 25. Okay, the last one will be 75 to 99. Okay, so that's the example of the C code. And the next, I want to see the MPI code. The MPI code, let's take a look at the MPI code. Let me just show one of the MPI examples. MPI, hello world. Right. This is a little hello world example, and MPI code. In the middle, I just create a message, hello world, from a rank, and calculate the message size, and open a file to write, and seek to the right location, and write. The location is, so the message will be in the order of rank, in the order of MPI ranks. Okay. So open the file, seek, and write, and close. Let's take a look at what will look like. So we do MPI CC. We'll just compile this code and compile this code to write C. So compiled, and we run. I just run this MPI. I just run this on local machine. I just start random number for processes. 17, which is not very good a number. Let's see what happened. Okay, it's done. So once it's done, let's take a look at. We have a new file created, hello-world.txt, and let's take a look at this content of this file and to see if the messages are in appropriate order. Let's take the content. And turns out that yes, although the MPI processes could be generated, could be launched in the random order, but in this file, which is written by individual MPI ranks, the messages are placed in the desired order by ranks. Okay, so I think I just stop here,